Last class we had done that
क्या
rule
हुआ?
किया था. Only odd harmonies are produced in closed organ.
Yes.
उधर से I think खत्म किया था F1 F2 F3 F.
Hmm. Now let's discuss about open organ pipe. Okay. Open organ pipe, it is actually both ends are open. Both ends are open. Like this type of pipe is there. So both ends are open means at both points they can vibrate with maximum amplitude. It's free to vibrate. So at both points you uh, will get antinode. So it will be like this only. At both points you get antinode like this. Like this type of. So this is also antinode. Here is also antinode, and here in between it is node. We know that between two successive nodes and antinodes, the distance is lambda by 2, and that is the length of the pipe. So here L is the length is basically lambda by 2. Lambda equals to V by 2F1. Here I am talking about fundamental mode. This is called fundamental mode. And the first fundamental frequency F1 will be equals to V by 2L. I know you understand that what is V is gamma RT by M naught. This is called as fundamental frequency. Fundamental frequency. Or we can also say it as first harmonic. First harmonic. In this, we have, as you can see, it is a V by 2L first harmonic fundamental frequency. If I go in higher mode, then what happens? If you see, if I'll go to find more harmonics, then what will happen? It will be here like this one, and here also you will get S1, and at this point it will be like this also. So what happens here? In place of one node, there are two nodes in between, and here antinode, here also antinode. So this is the next mode that we call it second harmonic. Now here antinode node, here again antinode. So one antinode to antinode is lambda by 2, other antinode to antinode is again lambda by 2. So this total is then in this fine you can say total L is equal to lambda by 2 plus lambda by 2 lambda. or you can also write as V by F2. So this F2 becomes here V by L. I can write it as 2 times V by 2L. Why? Because I know that V by 2L is the fundamental frequency. So F2 equals to 2 times of fundamental frequency. So it is second frequency that we are getting is second multiple of fundamental frequency. So we call it as second harmonic because it is second multiple. So it is called as second harmonics. And any frequency other than fundamental is called as overtone. So this is also called as first overtone. Similarly, if you want to find F3, you will get 3V by 4L. If you want to find F4, you get 4V by 4L, sorry, 3V by 2L, 4V by 2L. Similarly, F5 will be 5V by 2L. And if you want to find nth harmonic, then you can use NV by 2L. This 3 times fundamental, so this will be called as third harmonic. Also, it will be called as second overtone. This is fourth time, so you can say it is fourth harmonic, and this is third overtone. Here it is fifth harmonic and fourth overtone. Similarly, this would be called as nth harmonic, and it will be called as n minus 1 over. So conclusion, what is this here? That here we are getting third also, fourth also, fifth, sixth. So all type of harmonics we are getting. It means we can say that both odd and even harmonics are produced. Both odd and even harmonics are produced in open organ pipe. In open organ pipe. Understood, Neil?
Understood, sir.
Okay, you can write.
Yes, sir. Could you scroll down? Yes, sir. Done.
Okay, last this.
Yes, sir. Done.
Okay, here is one concept of end correction in both kind of pipe, open organ pipe or closed organ pipe. What happens if you have a closed pipe? Then the air does not stop at the top. It goes slightly above the surface like this, here, slightly above. So this length is called as E, that is called end correction. That means the total length of the tube is not L, it becomes L plus E. This I am talking about closed pipe. That's why fundamental frequency, if I have to write here. So we know the formula is V naught by 4L, V by 4L, but we don't write L only, we write 4L plus E. So this is the fundamental frequency with end correction. Fundamental frequency. Sometimes they say ignore the end correction, then you can ignore and we can do write the previous formulas. If you have an open pipe, then at in both ends it will be slightly go above like this, upside also and downside also. So here is also E and here is also E. That means the length of the air column becomes L plus 2E. That's why here fundamental frequency formula is V by 2L, but we write V by 2L plus 2 times of E. Or you can also write is as V by 2L plus 4E. So this is also fundamental frequency with end correction. You can write a note here also that what is E? E is actually 0.6 times of radius of the tube. Okay, here R refers with radius of pipe. Understood?
Yes, understood.
Yeah, so if end correction is there, then you can slightly change your formula.
Yes,
Right. हाँ बेटा, इस तरफ आओ।
Yes, sir. Done.
After that, next concept is about beats. Beats, what happens when two sound waves having slightly different frequency, slightly different frequency, uh, superpose, then beats may be formed. This I am talking about sound waves, of course. Let's suppose I have one sound wave is A sine omega 1t, and I have other sound wave as A sine amplitude we have kept constant omega. If you superimpose, then y becomes y1 plus y2. That is A, we can say it is sine omega 1t plus omega 2t. Sin C plus sin D का फॉर्मूला अगर हम लिखें तो we can say it is 2 sin C plus D. That means omega 1 plus omega 2 by 2 into T. Or cos C minus D by 2, it means omega 1 minus omega 2 by 2 into. So this is basically y equals to 2a cos omega 1 minus omega 2 by 2 into t, and this is sine omega 1 plus omega 2 by 2 into t. As the original equation was only having sine, so we keep the sine only, then this remaining terms will be like an amplitude only. So I can write y equals to a dash into sine. In place of this also you can write omega dash into t. So this is also a beat equation where what is a dash? A dash is this term that I have written under circle. This is 2a cos omega 1 minus omega 2 by 2 into. And what is omega dash? Omega dash is this angle, that is omega 1 plus omega 2 by 2 into. So अब बोलोगे a dash क्या है? So a dash is the resultant amplitude. Resultant amplitude, and this is not constant. As you can see, it depends upon time. So we can say that which varies with time, which varies with time at any point, at any position. So if you are standing at one place, so what you will feel that amplitude is becoming maximum, minimum becoming zero, So that is called as a beat. Like music, we see that one beat we hear, then there is a gap. Then again we hear the another beat. So that gap means at that point there is amplitude is zero minimum, and when you hear it at that time amplitude is maximum. First you write up to here, Neil, fastly.
Yes, sir. Done. Yes, sir. Done.
Here, if you see A dash that I have written here is 2A cos omega 1 minus omega t. Omega 1 you can write as 2 pi f1 minus 2 pi f2 divided by 2 into t. 2 2 it can be cancelled, so it is uh, in place in terms of f1 f2 you can write 2A cos pi f1 minus f2 into this you will find in the book. Now for maximum amplitude or maximum intensity, because yesterday I told that intensity depend upon amplitude. This cos term, this cos pi f1 minus f2 t should be plus minus 1, और ये 1 मिलता है आपको 0 पे, पाई पे, 2 पाई, 3 पाई, 4 पाई, 6 5 पाई, 6 पाई, यानी इंटीग्रल मल्टीपल ऑफ पाई. So it is pi f1 minus f2 into t is actually n times of pi. N you can take from 0, 0, 1, 2, any integer. Pi you can cancel. So at what time intensity will be maximum? T equals to n divided by f1 minus f2. That means if I keep on putting the values of t as 0, 1, 2, so first is 0, then 1 divided by f1 minus f2, then 2 divided by f1 minus f2, then 3 divided by f1. These are the time the intensity of sound will be maximum. The intensity of sound will be max. Okay, Neil.
Okay, sir.
Also, if you see the time interval between two maximum is called as is called as time period for beats, is called as time period for beats. दैट मीन्स टाइम पीरियड कितना हो जाएगा, दोनों को माइनस करोगे 2 माइनस 1 1 हो जाएगा, 1 बाय f1 माइनस f2 एंड इट्स रेसिप्रोकल ऑफ टाइम पीरियड अगर आप निकालोगे तो वो फ्रीक्वेंसी हो जाएगा. रेसिप्रोकल ऑफ t is called as beat frequency. It is called as beat frequency. That means beat frequency f will be equal to 1 by t. So 1 by t मतलब this will be f1 minus f2. ये सबसे important part है. तो ये बीट फ्रीक्वेंसी का मतलब है कि एक सेकेंड में कितना बीट आपको सुनाई देगा. दिस इज नंबर ऑफ बीट्स produced per second. Produced per second. ठीक है.
Yes. Yes, sir, done. Yes, sir, done.
Okay. Now the last topic of this chapter is after beats, it is a Doppler's effect. Now ये क्या है? So when there is a relative motion between a source and an observer, then there is some change in the frequency heard by observer. This phenomena is called as Doppler's effect. So if I say I have an observer, let's suppose this is an observer, and here is some source. Let's suppose this source is producing some sound of frequency f or f naught. The sound is traveling with the speed of v. Here I am, v is the speed of sound. And let's suppose I say that the observer is also moving. That means the first case that I am discussing, it is observer moving towards source, moving towards source, and source is at rest. Source is at rest. Source here is at rest, and it is moving towards the source with the speed VO. VO means velocity of observer. So now as we know that frequency, if you write velocity, relative velocity says that in opposite direction we should add the velocity. The frequency heard will be, you have to add the velocity of the observer, and then you can say it is a frequency as f. Now here I write the convention what I am saying. F naught is the actual frequency, actual frequency of source, V is speed of sound. V is speed of sound. V naught is speed of observer, and F is called as apparent frequency. Apparent frequency heard by observer. नील समझ में आ रहा है?
समझ में आ रहा है सर। यस सर। Yes, sir, done.
Now take it opposite case. If I say that observer moving away from stationary source, source is not moving. Like if I say here is the source, let's suppose, which is producing sound of frequency, and here is the observer which is moving away from the speed of sound. Now this is here v. Now you can see the relative velocity will be subtracted now. The frequency heard will be v minus v naught by v into, which is f naught, you can say. Now you know all about what is v naught, f. So again, I am not writing. So here it is subtract. Second case be that source is moving. Source is moving towards stationary observer. That means now observer is not moving. So if this is the observer, it is at rest, and the source which is creating frequency is moving with the velocity vs. F naught. Source effect you will see in the denominator. Okay, like here it will be v minus velocity of source and into actual frequency. Observer effect is in the numerator, source effect is in the denominator. Here vs is the different thing that I have written, and that is actually velocity of source. Neil, understood?
Yes, sir, understood.
Okay.
Sir, could you hold on? Yes, sir.
If I say that source is going away, source is moving away from observer. In that sense, let's suppose this is the source. It is going away with the speed of Vs. If observer is rest, sound is moving toward the observer only with the speed of V. In this case, here you have added, subtracted, so here you will add. So V by V plus Vs into F naught, where F naught is the. So you can clearly see that the frequency F will be less than F naught. So when the source is going away from the observer, then the apparent frequency decreases. Understood?
Understood.
We write this also, then we'll move some special cases.
Oh, yes, sir.
Sometimes they might give that source or observer, they are not, or let's suppose source and observer both are moving. Source is moving towards the observer. Observer is going away from the source. This is speed is Vs. Actual frequency is F naught. So what is the apparent frequency that is heard by the apparent frequency F? First, observer is going away from the source, so you will be V minus V naught. But the source is going towards the observer, so this will be V minus V. Just I have see, when the source goes towards the observer, in junction will become V minus Vs, and when observer goes away from the source, we do V minus V naught. So here both numerator and denominator you have to change, then you get your apparent frequency. Understood, Neil?
Ah, yes. Yes.
And if source is going away with the velocity Vs and observer is also going away, in that sense, you have to find the frequency. Observer is going away, V minus V naught into source is going away, then V plus Vs into. Please write these two cases also.
Yes, sir, done. Just could you show the statement above the apparent frequency level? Okay, okay, that done.
Yeah, here is no statement. Okay.
Okay, okay,
Okay, we'll continue this. I think this is complete only, but a little bit 5-10 minutes topic more there. Then we can solve problems. Okay.
okay, okay, sure. Okay. Thank you, sir.
Thank you.